Welcome to the second objective of the alternating series lesson, where we're going to be able to compute or calculate the error in an alternating series approximation. And look at these delicious looking gingerbread cookies. And it looks like they're all lined up, right? And then one's peeking out from the line. That has something to do with our alternating series approximation. So this is like I'm looking at the very next term in line, or the next person in line, the next term in the sequence. And what we're going to call that thing is the first neglected term, as we'll see. Okay. Now, when we go to try to find the sum of a series, which is like one of the goals is, hey, do they actually converge? And then the other one is, after you find out they do, what do they converge to? That second problem is a lot harder than the first one, unless it's geometric. Geometric, if it converges, as long as your common ratio, the absolute value, is less than 1, then we know that it converges specifically to a, first term, divided by the common, 1 minus the common ratio. Easy, it's a piece of cake. For anything else, though, what you have to do is look at partial sums, and the best that you can come up with is an approximation. And that approximation, well, we want to kind of know how far off we are. If you're talking about a Taylor polynomial, well, we have what's called the Lagrange error bound in order to bound the remainder for us to see how far off we could possibly be. And here it is. It's a little scary. However, that's not what this particular lesson is about. It's just showing you that, hey, in some other cases, we do have a way to bound the error, to see how far off we can possibly be. So if this thing right here, the little formula that's on the screen, if it confuses you or if it scares you, don't worry. The one for alternating series is far, far simpler. Okay, so let's say that we are going to try to approximate some sort of alternating series using a partial sum. And that partial sum, maybe I use 3 terms, 4 terms, 5 terms. I'm going to call it S sub n. And we're going to say that our sum, the actual sum of the whole entire series, well, it's only approximately equal to that partial sum, right? We still left off an infinite number. What is that infinite number of terms still going to contribute to our sum? So we're saying that, hey, it's just approximately equal to the actual sum. So if we added or subtracted a little something to our nth partial sum, I could arrive at the actual sum of that sequence or that series. And that thing that I add or subtract to it, we're going to call that thing the remainder. And it looks like this. I'm going to use an R, capital R, for the remainder. And of course, this remainder is going to be different depending on which partial sum that we stop at. The 6th one, the 7th one, and so on. So now what I'm going to do is I'm going to solve this equation for that remainder. It's very easy. I just have to subtract over that nth partial sum. And now remember, this could be positive or negative because these terms are alternating. So I'm going to take the absolute value of this. And this thing right here is the error. It's the remainder that's left over whenever we approximate an alternating series, or any kind of series really, with a partial sum, okay? So specifically for an alternating series, we can bound that. Like, this is something we can get a handle on. We can see how big that possibly could be, this remainder. Not exactly, because if you can get it exactly, then you know exactly what the sum of the whole entire series is. But we can see what it's less than. So take a look at some pictures that we saw back in the first objective. So in this first picture here, you can see, of course, that what I've got is the partial sums. The first one, S sub 1, that's the first term. And then I'm going to take away the second term, and then I arrive at S sub 2. Then I'm going to add in the third term. I'm going to arrive at S sub 3. Then I'll take away the fourth term, and I'm going to arrive at S sub 4. And of course, I can see that I'm bouncing back and forth, getting closer and closer to the actual sum of the series. Okay, so let's say, for example, that I'm going to approximate this series sum with the fourth partial sum. So in this case, it's just this number that's right here. It's the first one minus the second one plus the third one minus the fourth one, right? All right, so how much I'm off by, the absolute value of that, we're going to call that the remainder. And let me just highlight something here. That right there is the remainder. It's the difference between those two things. It's the difference between the sum and the fourth partial sum. It's that distance. And I'm going to show you in a second that that is less than the next term in the sequence, the fifth term, which is what we like to call the first neglected term. We went up to the fourth one. The next one that we have neglected is the fifth term. And we're saying that this remainder is less than or equal to that. Let me show you that very, very easily back over here. So again, hopefully it made sense to you that what I'm doing is I'm subtracting s minus s sub 4. Here's my s value, and here's my s sub 4. I'm subtracting those two things. When I subtract it, I get a distance, right? It's just like the difference in x's. It's x sub 2 minus x sub 1. I'm getting this little distance that's right here. Okay, and now I can easily grab this little distance. Now, let me just drag it right up there. Let me drag it. And now compare it to the next term. I compare it to the next term, which is the b sub 5 term. And you can see that the difference between s and s sub 4 is definitely smaller than b sub 5, which is the next term in the sequence. That's very, very useful. All right, let's look at another one of these. So let's say that I was going to use the first 5 terms in order to approximate the sum of this alternating series. Well, the remainder here, again, is equal to the difference between the sum and the fifth term, or at least the absolute value of that, which means, of course, I just want to subtract those two, s minus s sub 5. It's just a little distance, and that distance, if you compare it, you look it straight up, it's less than the next term, which is b sub 5, the first neglected term of the sequence. I went up to the fifth term, so the first neglected one is going to be the sixth one. So again, I'm going to go back and show you this distance one more time. Well, that's the calculator. This distance one more time right here, but this time in blue. Yep, in blue. All right, so again, if I subtract s minus s sub 5, I get that little segment length. Let me just drag that little segment length up. I can see very, very clearly it is less than the next term in that sequence, this b sub 5. And that's what we're saying, that that's as big as we could possibly be off for our sum is the next term in the sequence. And that brings us then to the formal statement of the alternating series remainder. If a convergent alternating series satisfies the condition that a sub n plus 1 is less than or equal to a sub n, in other words, the terms are decreasing, and that's why the picture that we were looking at made sense, because our terms are decreasing. I'm subtracting or adding a little bit less than I had from the previous term. The absolute value of the remainder, r sub n, involved in approximating the sum s by s sub n is less than or equal to the first neglected term. I went up to the nth term, so I look at the very next one, which is the n plus 1th term, and that's as big as the error could possibly be. I went up to, I approximated my sum using only 4 terms, so I'm going to look at the 5th one, and that 5th one will say that's as big as the error could possibly be from our actual sum. All right, so I'm gonna stop the video right here so you can digest that for just a second, and then we're going to come back and take a look at a couple of examples to put this into practice.